Okay, hello everyone. My name is Jacob. Welcome to our webinar. Today we are going to be discussing the use of SCR systems for CO2 augmentation in greenhouses. So this presentation should take approximately 30 minutes, followed by questions and answers if you have any. Just so you know, everyone else except me is currently muted. At the end of the presentation, we will unmute everyone and we will go into questions. So let's jump right in. So basically what we're going to talk about today is CHP and Greenhouse Applications, the basics behind CO2 augmentation for greenhouses, the use of SCR technology and the safe integration for CO2 augmentation. And then specifically, we will talk about Safety Power's EcoCube SCR system and its controls. And then we'll also talk a little bit about recommended monitoring technology. So before we get into the greenhouse and CO2 augmentation aspect, I'll just start with a brief introduction. And we will have some standard slides that we'll go through, but the focus of this webinar isn't the basics of SCR technology, it's the specifics of CO2 augmentation. So I'll go through a lot of these very quickly and we'll focus more on CO2 augmentation. If you are interested in the basics of SCR technology, we do have other webinars recorded and they could be seen on our website under videos. So Safety Power is a leading manufacturer of emission control systems for large diesel and natural gas engines. We have a strong regulatory knowledge and the capability to meet stringent global standards. And we've proven this with over 200 SCR installations in North America, and we have experience with all engine makes. That's Cat, Cummins, MTU, GE, Jenbacher, and others. In addition to SCR, many of our installations have also oxidation catalysts, diesel particulate filters, and integrated silencing into one compact housing, which we call the EcoCube. As a side note, diesel particulate filters are only used for diesel engines. In the case of this presentation, we'll be focusing on natural gas engines for CO2 augmentation, so we won't really be talking about DPF. Additionally, we do provide industry-leading ongoing support with remote monitoring, and we have extensive experience with accessories associated with SCR technology, such as air compressors, urea transfer systems, etc. Our headquarters are located in Mississauga, Ontario, which is a suburb of Toronto. This is where our sales office and engineering office is. We do all of our project engineering here, as well as some of our R&D, which would include things like CFD modeling for mixing models and software development and other things as well. We also do some fabrication here, so we do fabricate our SCR injector lances here, our instrumentation clusters, and our control panels, as well as some other small components. The EcoCube reactors themselves are manufactured in Kitchener, Ontario. This is a 40,000 square foot facility located approximately an hour away from Toronto. This is also where we would do all our quality checks and final integration. You could see here on the right, this is a whole production line of 2 megawatt size engines. And of course, all of these are pressure tested and all our welders are certified welders. We are an ISO9001 certified company. Quality is something that's very important to us, and our certification encompasses everything that we do, everything from sales to project management to manufacturing and ongoing support. In the context of natural gas gensets, the primary emissions of concern are carbon monoxide, CO, unburned hydrocarbons, or VOCs, and NOx. So oxidation catalysts can be used to reduce carbon monoxide and VOCs. and this would essentially reduce the odor as well. Unlike SCR technology, oxidation catalyst is a passive technology. SCR technology is an active technology which requires efficient control and monitoring, and this is used to reduce NOx, and this is Safety Power's specialty. In addition, there is engine noise, and we treat engine noise as basically just another emission which can be reduced, and our systems do come with integrated silencing as well to deal with the exhaust noise of the engine. So that was just a brief, quick introduction, and now we'll jump right into CHP and greenhouse applications. So plants, as you know, need a number of things to grow. Besides water, they also need light. In the case of greenhouses, especially modern greenhouses, they wouldn't just rely on sun, they would rely on artificial lighting for optimal growth and lighting, which of course requires quite a bit of power. Additionally, plants would need heat and CO2 for photosynthesis. So CO2 is present in ambient air, as we all know. It's present in concentrations of approximately 400 parts per million. However, inside a greenhouse environment where the plant's density is quite high, and of course you would have the optimal lighting and the optimal temperature, so plant growth is also very high. In those sorts of environments, the consumption of CO2 can be higher than CO2 gets replenished. And so in a typical greenhouse environment, CO2 concentrations are usually as low as 200 parts per million. And according to the Greenhouse Growers Handbook by Andrew Meffert, ideal concentrations of CO2 for many crops are actually between 800 to 1,000 parts per million, depending on the crop, sometimes higher. And if you achieve these concentrations in combination with ideal lighting and ideal heat, productivity and growth can be increased by as much as 50%. So there's a definite and proven benefit to increasing the CO2 concentration in greenhouses, and this is something that's been done for quite a while now. And so the sort of traditional greenhouse design relies on three separate sources for heat, for CO2, and for power, where heat is derived typically from a boiler. CO2 is usually fed from a pressurized tank with liquid CO2, and power would just be provided by the electric grid. But there's a number of disadvantages with this sort of approach. Pressurized tanks are quite expensive. They need to be stored somewhere and regularly replaced. And grid power is becoming increasingly more costly. The overall efficiency of this sort of design is approximately 45%. The other problem, of course, with relying on the grid is power outages, which can be absolutely devastating to crops and could set back production months and be a huge, huge cost. So for this purpose, most, if not all, of these traditional greenhouses also come equipped with diesel engines for backup power. So even this traditional design already has gensets on site, typically. So an alternative approach is to use a natural gas or other gas-burning genset for your primary source of power. This helps remove reliance on the grid and provides power, usually at a lower cost. If used strictly for power generation, a modern natural gas engine should output an efficiency of around 45 to 50%, depending on the engine, where the majority of this energy is lost, of course, in the form of heat. And this is where combined heat and power, or CHP, comes in. So heat from the engine block and the exhaust can be captured with heat exchangers and used to keep your crops at optimal temperature levels. This can increase the engine's overall efficiency to 98% or even higher, and is a great way to maximize your investment. But this can be taken even a step further. Engines also happen to produce large amounts of CO2, which plants need. So with the use of an effective emission control system equipped with SCR and oxidation catalysts, it is possible to clean the engine exhaust and feed CO2 to the greenhouse. This results in a pretty nicely engineered system where the engine product, being power, as well as most of the engine waste, as the CO2 and the heat, is being utilized. So in this slide, we go into a little bit more detail specifically about CO2 augmentation and the use of SCR technology for this. So the primary component, of course, that you see here is the genset, but also the emission control system and heat exchangers. So as a rule of thumb, a natural gas engine will produce approximately 0.2 kilograms of CO2 per kilowatt hour input. But this will vary per engine, of course. A minor nuance is that CO2 is only needed during photosynthesis, which occurs during the day. Simultaneously, heat is typically needed most at night when it's coldest, but that will depend on the geographical location. And so therefore, these sort of installations typically operate in conjunction with a buffer tank to store excess heat during the day and then use it at night. That's not a necessary part, but an optional. There will also be a bypass damper valve, which must be used, and then basically when CO2 is not needed or when the exhaust is potentially not clean enough, the damper valve will be closed and the exhaust will simply be directed to the stack and released into the atmosphere. And then, of course, the greenhouse would still receive the electricity and heat that it requires. Typically, 2 heat exchangers would be used. The first one to cool the exhaust to a little over 100 degrees Celsius, and then the second heat exchanger to cool the exhaust down to an acceptable below 50 degrees Celsius. Cooling to this level would remove most of the moisture in the exhaust, and then the CO2-rich exhaust can be easily transported to the greenhouse through PVC pipes. As mentioned, the exhaust would be typically transported through a damper valve located in the stack. When the valve is opened, a blower is also engaged for 2 purposes. One, to dilute the CO2 gas, which would be usually in very high concentration, and also to help distribute it through the greenhouse. The CO2 set point is generally measured in the greenhouse, and if the set point is reached, the valve is closed. If the set point is below, the valve is opened. Another key feature not pictured here is the gas extraction analyzer. This is something that Safety Power now manufactures in-house, and you could see a couple of the key features here. So it comes as a standard with CO, NO, and NO2 cells, although additional cells can be added pretty easily if required. It includes a refrigerant dryer, a pump, and all necessary controls to ensure good gas conditioning and sampling. It is easily integrated with our standard CP100 control panel, but it interacts primarily with the damper valve. So basically, it would be taking CO, NO, and NO2 measurements within the greenhouse and before the greenhouse, and then depending on what it measures, the bypass valve will either be opened or closed, and then the CP100 panel controls the emissions, the NOx out and everything separately. Fan gases are also housed within the panel for easy sensor calibration, and that's just for convenience. And one thing that also should be said is this unit is specifically designed for CO2 greenhouse application. Many of our competitors will also use a similar system for their emission controls, for their NOx reduction. In our case, it's not required, everything is built into our standard CP100 control panel. So this would only be required for projects with CO2 augmentation, not standard projects. As an additional optional item, we can include a high-temperature ethylene analyzer. We would use the same sort of equipment as traditional European SCR suppliers, but this would only be required for certain types of crops. In most cases, you would not need it, but we can offer it as an option. So now on to the basics of SCR technology and safe integration for CO2 augmentation. And by the way, I do have questions. We're going to take questions at the end, but you could type out your questions right now. We'll have a look at them, and then we'll address them later, just so that you don't forget. So as I mentioned at the beginning, this isn't about the basics of SCR technology. We do have other webinars which focus on the basics of SCR technology. So if you want to learn more about that, those are available on our website, but we will run through these slides in this presentation relatively quickly. So here we have a simplified diagram of an SCR system. Basically, as you can see, it relies on urea and compressed air. And essentially, as the exhaust gas enters the mixing section of the SCR system, urea and compressed air is injected and mixed with the exhaust gas. And then as this mixture enters the SCR catalyst section of the reactor, a chemical reaction occurs which reduces NOx into nitrogen gas and water vapor. One unique thing that you might notice here is that there's two NOx sensors, one upstream and one downstream of the SCR system, and that is something that Safety Power does for both upstream and downstream control, feedback and feed-forward control. The traditional Siemens SCR design was developed in the 1980s, and you could see an example of that sort of installation there. And the key thing here is that the traditional design includes a separate mixing tube, separate from the SCR system itself, which takes up quite a lot of room and is quite costly. At Safety Power, we've developed the EcoCube SCR system, which incorporates the SCR system and the mixing tube all into a single housing. And in addition, this includes all the other items that you saw in the previous slide. There was also a bunch of interconnecting piping and a silencer. So all of this, the SCR, the mixing duct, the integrated silencing, in addition to the diesel oxidation catalyst, or oxidation catalyst in this case, sorry, is all included in a single housing. The EcoCube does have a number of features that sets it apart from its competition, part of which is its housing is constructed from stainless steel. I mentioned this already as well, but the mixing duct, of course, is integrated into the SCR housing itself. For precise control, it comes standard with two solid-state automotive-type NOx sensors. For ease of installation, we include a junction box, which you could see at the front of the reactor here. Basically, there's a number of sensors, pressure sensors, temperature sensors, NOx sensors, all through the reactor, and they're all fed to this one junction box, which simplifies commissioning installation significantly. The reactors also come factory insulated, so they're shipped to site already insulated with 3-inch mineral wool and aluminum cladding. The catalyst, it also comes shipped with the catalyst inside as well. And then we've added certain features over the years as well. So for example, for enclosure installations, we include worker safety arrest rods that you could see at the top of the reactor here. So these are so that workers can attach themselves to while working on the enclosure for safety purposes. There is integrated silencing. In most of these reactors, it comes standard, and we could beef it up as well to higher levels if needed. We do have an in-house sound expert, and we're capable of quite a bit of analysis in-house. And then for rooftop applications as well as enclosure installations, we use a sloped reactor roof, and that's just so that rain and snow does not accumulate on the reactor itself. Now a couple of words about controls and monitoring for CO2 augmentation. So our control panels, for our control panels, we use industrially hardened embedded controllers, which allows for much more functionality than a standard PLC. For one thing, it allows us to, instead of just doing load following sort of controls, we do model-based controls based on our mixing models, which allows for much more precise and much more quickly recovering controls. And I'll show you an example of that in just a little bit. It also allows for things like historical data archiving and remote monitoring, which is very important for ongoing support and has really helped set ourselves apart from our competition. A couple of words about the NOx sensors that we use. So I did mention we use automotive type solid-state NOx sensors, and these are much more rugged than electrochemical type cell sensors. Those tend to break down much more often. Solid-state type sensors are much more durable. But more importantly, they have a much quicker response time as well. So electrochemical type sensors, they'll have a response time of, at best 30 seconds, around that range, whereas solid-state sensors have a response time in the millisecond range, which is a very key factor for engines which will have varying NOx emissions, and which is very, very common as well. So this helps us recover very quickly with our reductions. And this is a patented design as well. One thing that you'll notice is it's unique as well is the shape of the sensor itself. And the reason for this is we have separate holes, so 7 separate holes in different locations, which allows for an average measurement of the whole exhaust stream as opposed to a point measurement. So it's also a much more accurate measurement as a whole. And so in this slide, we'll just show an example of why all of this sophisticated control and these solid-state sensors are important and what we get out of this. So this is an example of an actual installation that we have. This is an actual engine. And the top graph here shows basically the raw NOx exiting the engine. And the bottom graph shows the engine load at the same times. And so what you'll notice a couple of things, but first of all is that the engine load is reasonably constant, approximately with 2% fluctuation. But despite that, the NOx fluctuates almost as much as 50%. So if all you were doing is load-based following, it would be very difficult to achieve the required reductions, especially stringent reductions, the sort of which are required for greenhouse applications. And the other thing you'll notice is that these are relatively small intervals. So between these lines, we have 2-minute time intervals. So if you had a NOx sensor with a response time of 30 seconds or more, you wouldn't be able to recover on time to consistently have the levels that you need. And those little spikes can, for greenhouse, potentially be dangerous. So this is basically the results of all our controls. The average NOx out of our system for the same installation during the same period is an average of 4.4 parts per million, which is very, very low. You'll also see that there are some peaks here and there, but they recover very, very quickly, and that is due to these solid-state sensors. As a side note, I'll mention our electric preheat system. So this might not be necessarily relevant to greenhouse applications, but it might be in certain cases. Typically, these are used for installations where an air permit is required. So because of the large thermal mass of the SCR catalyst, there is a certain heat up time, and the chemical reaction is only activated above 300 degrees Celsius. So that heat up time, depending on the size of the system, can be 30 minutes, sometimes more, which for air permits, a lot of the time, that's not acceptable. In the case of a CO2 augmentation project in a greenhouse, that might be okay. You would just have the damper valve closed during that time, but maybe you'd prefer to have an electric preheat system, which would allow you to reach activation temperature in less than 5 minutes. So this is something that might be of value to a customer, depending on their preference. The last thing I'll talk about is product support, which is important with all our prime power installations, and CO2 augmentation projects would, of course, not be an exception. So all our control panels come equipped with an internet router, and which allows us to provide remote monitoring. So all our dedicated technicians located in our head office here, they basically have access to a software that we call Worldview, where we see what basically the operator sees on our panels remotely. So anytime there's an alarm or a fault, we can quickly respond, and we could provide the same access to the operator as well. So your operator can view the control panel remotely. And this is very important because it allows us to diagnose small problems remotely. So according to our maintenance team, most of the time when a site visit is requested, it's for something minor like a sensor failure. And this is something that could be diagnosed remotely, and then instructions can be given to the operator to provide a fix, and a part can be shipped and replaced. So this would just save you a maintenance visit, and most importantly, downtime. So this is something that's really set us apart. We're also able to make patches online, right, which is important, so we can provide temporary fixes and then do the necessary work on site if required. And this sort of remote monitoring and the service that we provide is something that's really set us apart in the U.S., and it's brought us a lot of business because of customers essentially being frustrated with European support, which can be a little bit slower. And of course, we are local in the sense that, you know, we are in North America, and our office is located very, very close to an airport, and when we do need to come to a site visit, we could be there relatively quickly. Of course, we also stock a majority of our components on site for next day delivery if needed. So that's essentially what I wanted to cover for the basics of CO2 augmentation for greenhouses.